Hi everybody, this is Gigi from Hawaii Community College. In this video, we'll be talking about the polynomial approximation for functions, or you can actually call these the Taylor polynomial, okay? So depending on what your teacher wants to call that, but I like to call that polynomial approximation because that's what we're going to do in this class, approximating functions using a polynomial, okay? So suppose you have, say, a function f of x is equal to square root of x. And we have learned from Calc 1 that when x is near x equal to 4, well, we know that square root of 4 is 2, right? But for any function value, x value, say x is right here, near 4, what is the function value f of x at this point? Okay, so that's the question. And in order to answer that question, we could use in Calculus 1, you have learned that you could approximate this using the tangent line, right? Because we could find the equation of the tangent line. So then the function value of the line is going to be approximately the function value of the square root of x at that point x near 4, right? So let's see how that equation of a tangent line comes about. Let's remind ourselves here that we know the slope is y, the difference in y minus divided by the difference in x, right? So but we know m, the slope, is going to be the slope of the tangent line. Well, slope of the tangent line is the derivative, and we've learned that from Calc 1. So we can see that the derivative at 4 is going to be equal to, so y minus y2 minus y1, right? So we have y minus the y value that I know, which is 2, and then over x minus 4, the x value that I know, and that is 4, right? Plug it in the point to find the equation of the line. Multiply both sides by x minus 4, and then add the f of 4 over. We will see that the equation of the tangent line is y equals f of 4 plus the derivative at 4 times x minus 4, right? So we are talking about the function square root of x. So the derivative really is 1 over 2 square root of x, right? Now, then we would go ahead and evaluate that at 4. So then this right here is 1 over 4 times x minus 4 plus f of 4 we know is 2, right? So this is 2 equals y. Clean that up. You will have y is equal to 1 over 4x plus 1. Okay, that is the equation of the tangent line, and we call that the linear approximation of function values near 4, right? So how near is near? And that's something that we're going to discuss in this chapter. How near is near 4, okay? In other words, we can summarize that the linear approximation, I'm going to call, instead of y, I'm going to call that L of x, right? That's the linear approximation of any function is f of a now at any given point a is f of a plus the derivative at a times x minus a. And you've seen that before, right? What is this linear approximation good for? Well, you also have seen that we use the linear approximation to approximate function values. For example, near 4. So suppose x right here near 4. Suppose x is like, say, 4.1. Okay. We want to know what is square root of 4.1. What is square root of 4.1? So square root of 4.1 we can approximate that being the linear function evaluated at 4.1, right? The linear approximation is 1 over 4x, 4.1 plus 1. If we throw that into our calculator, we're going to get a value of 2.025. Okay, so that's using this linear approximation, this right here, or we would say the equation of the tangent line to approximate that value, square root of 4.1 being 2.025, right? Now, if we use our actual calculator, the calculator will give us a value of square root of 4.1 being 2.024845. So this is a pretty good approximation. And that is because 4.1 is close to 4, right? So linear approximation is being used for values near the point A. So near A. How near is near? We're going to discuss that in this later in this chapter. All right, so that's the linear approximation, and that is a quick review of Calc 1. Okay, now here in Calc 2, what we want to look at is the polynomial approximation. Okay, but before we go on to polynomial, let's look at one step up from linear. So this is linear, right? So remember, the linear approximation is that. Okay, now let's take a look and learn from here, from this lesson here. Now, if we, so here is A, right? And that function value right here is L of A. And L of A is also the same as the function value F of A. Right? So from there, we can see that L of A is the same as F of A, which is that point right there, where the point of tangency is. Okay? Now, let's take the derivative from this on the left and from the right. The derivative of F of A, which is a constant, is 0. The derivative of this right here is just going to be that constant F prime of A. Right? So, not only with the linear approximation, not only that L of A is equals to F of A, we also have L prime of A, the derivative of that linear approximation, is the same as the derivative of the function value. And those are the characteristics that make this linear approximation the best fit, the best approximation near A, right? So if we were to move on to a quadratic, what do you think? What property do you think a best quadratic approximation Q of X also must have? Okay, you have it right if you say, well, the second derivative of the quadratic approximation is going to have to equal to the second derivative of the function at the point A, right? So keep that in mind, and we're going to go ahead and take a look at that quadratic approximation. So the quadratic approximation will look like this. Here is the linear part, right? And then you'll have to add on some constant c times x minus a squared. That's what makes that a quadratic. Okay, now suppose we go and take the derivative of both sides. The first derivative, well, the derivative of f of a is a constant. F of a, the constant, the derivative of that is 0. And the derivative of f prime of ax, if you think about distributing this out, you'll have f prime of ax, and the derivative of that will just be f prime of a. And then the derivative of this quadratic part right here, bring the 2 down, you'll have 2c times x minus a to the first power, right? Now, let's take the derivative one more time. So the second derivative of that quadratic approximation is this now is a constant. So the derivative of that is 0. And then the derivative of this part right here of the linear is just the 2c. Okay? So remember, we said the second derivative of the quadratic approximation is going to have to equal to the second derivative of the function at the point a, right? So then if we put in f prime double prime of a right here is equal to 2c, and we solve for c, c is going to have to be the second derivative divided by 2. Yeah? All right, so then you will see now that the quadratic approximation of a function is f of a plus f prime of a times x minus a. That's the linear part, right? The linear part, okay? Plus c, which is this right here, okay? F prime of a times x minus a square, and that is the quadratic approximation for the function f of x. Okay, now why do we want the quadratic approximation? Well, if the linear line, if that line that was right here, if linear wasn't good enough of an approximation, we may want a quadratic, right? Now, we may actually even want a polynomial of like 4th degree, 5th degree. It depends how close of an approximation we want to have, and it depends on the curvature of the function. All right. So for the square root of x, I think linear approximation would be pretty good, right? But if we want a closer approximation, we might want a quadratic. So for example, again, let's say that f of x is equals square root of x, right? And then so the first derivative is going to be, the first derivative of x is going to be 1 over 2 square root of x, right? Which really is, and then here's the second, this right here really is 1/2 x to the negative 1/2, right? So then the second derivative is going to be negative 1 over 4 x to the negative 3/2, which is negative 1 over 4 square root of x to the third. Okay, so let's go and evaluate these values when a is, say, what did we do before? A was near 4. Let's do that near 4. Okay, near 4. Near 4. Okay, near a equals 4. So then f of 4 we know is 2. F prime of 4 is 1 over 2 square root of 4, which is 1 over 4. The second derivative now at 4 is negative 1 over 4 square root of 4 to the third power. Okay, 4 to the third power. Oh, 4 times 4 times 4, that is 64. Square root of 64 is 8. 8 times 4 is 32. That's negative 1 over 32. Okay, so the quadratic, we would say the quadratic approximation of square root of x is going to equal to 2 plus 1 over 4 times x minus 4 minus 1 over 32 times x minus 4 to the third power. Okay, now from previous example, we saw that the linear approximation, which is this part alone of square root of 4.1, right, was going to be 2.025 as the linear part. And then now we got to minus out 1 over 32 times 4.1 minus 4 to the third power. Okay, so that is going to be 0.1 to the third power divided by 32, and that is a negative number, plus 2.025, and that is going to give us 4.1 is approximately 2.02496.875. Okay, now remember the calculator. When we use the calculator, calculator give us a value, square root of 4.1 being 2.02485, right? So I think then using a quadratic approximation give us a closer answer to our calculator answer, which is what we would say that our calculator knows polynomial approximation pretty well, right? So my question to you is maybe to ponder, how far do you have to go to get to this value? Meaning, which polynomial approximation should you go to? What degree polynomial should you go to get to that value right there? All right. So, and there you go. That is the polynomial approximation. I mean the quadratic approximation. Now, let's think polynomial. Okay, and we could actually name this the Taylor polynomial for the person who thought of this topic here. Okay, Taylor polynomials is that what we call that. Okay, now suppose let's say we just think of like fourth degree, just so we can examine what's going on here. Okay, now fourth degree. Well, let's say that we go and take the first derivative. Okay, the first derivative is going to be f prime of a plus a bunch of stuff in between. And I'm going to focus on this part right here because I want to know what that constant is. Like, can I generalize what that constant is based on the nth degree polynomial? Okay, so if I was to take the first derivative, I would have all that plus bring the 4 down. So I will have 4c times x minus a to the third power, right? And then I'm going to take the derivative again. So then the second derivative is going to be, okay, and you'll have a bunch of stuff here. And I want to focus on this part right here so I can see maybe a pattern that has to do with the nth degree polynomial. So I already have 4. Now I got to bring down 3. So 4 times 3 times c to the x minus a to the second power. Yes, that's for the second derivative. And then the third derivative, I am going to have things here plus I already have 4 times 3. But then what am I going to have to do? Bring the 2 down, right? So I will have 4 times 3 times 2 times c to multiply by x minus a. Okay, and then the fourth derivative, and this is the fourth degree polynomial, so the fourth derivative is going to be a constant, right? It is going to just be, there's no more of this stuff here. It will just be 4 times 3 times 2 times 1 times c, and that's it. So this right here, as you can see, is 4 factorial times c, right? Now, we say that this fourth degree polynomial is the best approximation when the fourth derivative is equal to of the polynomial, the fourth derivative of the polynomial is going to have to equal to the fourth derivative of the function value at a, right? So then c is going to have to be c for that constant right there is going to have to be fourth derivative divided by 4 factorial. Okay, so that's the pattern that I have just observed there. In other words, that constant c for any nth degree polynomial, okay, is going to be, and I'm going to call that c sub k, that kth coefficient is going to be the kth derivative divided by k factorial based on the pattern that I have observed there. Okay, and so if you think about that fourth degree polynomial approximation, or the nth degree polynomial approximation, is going to be, there's this linear part, right? And then here's that quadratic that you have seen. And then if we want to add more, we would just be saying the third derivative, right? Third derivative divided by 3 factorial, x minus a to the third, all the way up to the nth degree polynomial derivative, nth derivative at a divided by n factorial times x to the minus a to the nth power. And that is the nth degree Taylor polynomial approximation for a function f of x. Near a. Okay, and again, how near is near? We will talk about that in the later unit. All right. Now, if you actually think about this for a second, this is a sum, so we can use the summation notation. So I can say that the nth degree polynomial is going to be the sum from 0 to n, okay, of c, that coefficient c sub k right here, that is c sub k right here. The coefficient multiplied by x minus a to the kth power, where the coefficient is going to be the kth derivative divided by k factorial. Now, one thing that we want to know also, by definition, 0 factorial is equal to 1. And so is 1 factorial is also equal to 1. So by definition, 0 factorial is 1. Remember that. So when you plug in k equal to 0, remember the denominator is not 0. It is 1. And that is okay. Okay? And so that right there is our nth degree Taylor polynomial of a function near a. Okay, let's use that. Find the fourth degree polynomial approximation for e to the x center at a equal to 0. Okay, we're going to start out slow. And this is particularly is a good first practice because the derivative of e to the x is e to the x, right? That's great. So near A, and A is equal to 0, so you will just have e to the 0 power, which is just 1, right? So then here, C, the first coefficient, the initial coefficient, is going to be 1 over 0 factorial, and we said 0 factorial is 1. So it's 1 over 1, or we say that is 1. All right, first derivative evaluated at 0 is 1. So then C1 is going to be 1 over 1 factorial, and 1 factorial is 1 also. So you will have 1 over 1, which is 1. E0 is 1, and so C2, the second coefficient, is going to be 1 over 2 factorial, which is 1 over 2. Okay, and then again, this is going to be 1, and this again is going to be 1, right? So C3 is going to be 1 over 3 factorial, which is 1 over 3 factorial is 6. And then C4 is going to be 1 over 4 factorial, and that is 1 over 24, right? So the polynomial, that's not it. The polynomial P4 of x is going to equal to center at 0, so you will have 1 plus 1 multiplied by x minus a. A is 0, so it's just x, and you don't even need to write the 1 there. So it will just be 1 plus x plus 1 over 2x squared plus 1 over 6x to the third plus 1 over 24x to the fourth power. Now, if you think about the pattern of where this goes, what do you say Pn of x is going to be? We're going to have to focus on this for that pattern, right? So look at this right here for that pattern. You will have sum, because we are adding, and that's going to go from 0 to n. And x is going to be x to the n power, because right here we're going to have x to the 0 plus x to the first, and this is 1 over 0 factorial. This is 1 over 1 factorial, and then plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third, and so on, plus 1 over 4 factorial x to the fourth, right? So on the numerator, you will have x to the n power. On the denominator, you will have, actually, say k, and k will go from 0 to n, and this would be k factorial on the denominator. So that right there is the nth degree Taylor polynomial of e to the x near 0. Okay, so make sure you make this chart to keep you in, kind of keep everything in order. Okay, so here we have another problem for you. Taylor polynomial ln of x plus 1 center at a equal to 0 we'll put the chart up. Okay, so just follow this chart. Pause for a second, fill in the chart, and go ahead and put together your polynomial. The answer is right there for you to see. All right, and that is it.